angular momentum, angular velocity, omega is just our change in angle over a change in time. Multiply that by our angular mass, I, or our rotational inertia, and we get our angular momentum. And then how do we change angular momentum? We apply a torque over time, and torques are created by forces. But not just any force, they need to be a force with a perpendicular moment arm. So the force needs to have some leverage, I guess is what we would colloquially say. And the larger that R, or the more perpendicular it is, the stronger the torque created by the force. And all of these are vector equations, meaning that they have a magnitude and direction. And we know that the direction is determined by the right-hand rule. And in general, things that if you reverse the direction of rotation, you change the sign. We haven't really done this. We'll do a little bit of it conceptually, like we won't do any calculations. But these do work just like any other vectors. It doesn't just have to be like plus and minus along one axis. You can rotate an angular momentum vector. You can do a bunch of things to it. So these vectors are just normal vectors. There's nothing special about them here. They just have this kind of weird relationship to what's physically happening, which is the right-hand rule. Okay, so we've also seen how this is extremely analogous or completely analogous to the linear momentum framework. And all of these equations should look familiar, except maybe the velocity, the relationship to linear velocity and angular velocity. That we'll do at the end of lecture today. We already have the tools to do that. It's just a fun little add-on. And then also this kinetic energy row. So I don't think we've talked about it explicitly, but there is rotational kinetic energy, and the expression is extremely similar. We just swap out the m with I for our rotational mass or rotational inertia, and we swap out the velocity with angular velocity. So you won't be assessed on that, but it's just good to know that rotational things do have energy associated with them as well. Okay, rotational inertia, we talked a lot about this last time, but you calculate it by adding up the contribution to each mass element associated with the object, and that contribution for each element is its mass times its distance from the axis of rotation squared. So again, we've seen a lot of examples of this. We see that the arrangement matters and the axis of rotation matters, because if you change the axis of rotation, you're of course going to change the distance of all the mass elements to that axis of rotation. So let's do a quick little example of that. I know this is something you did exactly in DL, but I'm going to spin myself and give myself a certain amount of angular momentum, and then I can't change the total angular momentum after that point. I mean, there is a little friction here, so you'll see I slow down a tiny bit. But in general, once I pick my feet up, there's this system of me and the weights in the stool has a constant angular momentum, and so anything I do might have some effect, but no matter what, the total angular momentum has to stay the same. Right? So first, I'm going to spin myself. I have some angular momentum. I'm spinning. And now if I put the weights further out, we notice I slow down. And the reason being is that I increased the system's rotational inertia, right? These two weights, I mean, my rotational inertia is something, but it doesn't change, I guess my arms. But these two weights are really what's changing. And they both have a mass m, and when I hold them close, the r is very small. And so the contribution to rotational inertia from these is small. And so some I omega, that's the angular momentum that we have. And then when I push my arms further out, move the weights further, the r grows, and so the mr squared gets bigger. And so the angular or rotational inertia of the whole system grows. But if L stays the same, then I has to decrease. Or sorry, if L stays the same, then omega has to decrease because I increased, right? And the opposite works too. So if I spin myself with some initial angular momentum and then decrease my moment of inertia, the angular velocity will increase. So the subtlety, the one thing I wanted to add during this lecture, is that it's the distance from the axis of rotation. It is not the distance from like some point, right? So when I spin on this stool, the axis of rotation is this infinite line going up through the center of the stool, up through my spine, through my head, right? That's the axis. And so what that means is that when I say that the distance from the axis matters, is that if I change the height here, it makes no difference, right? I am moving these, but since like the axis of rotation extends all the way up and down, and so this vertical distance does not matter at all. It's just the distance from this central axis that matters. So really you could say this is like R perpendicular if you wanted to. And that's when you draw this R, it's only the piece that's perpendicular to the axis of rotation that matters. If I took one of these M's and I like just moved it up along this axis of rotation that we see here, it'd make no difference. Okay, so we'll see a couple more examples that display this. Here we have the moment of inertia of a bunch of different extended objects about different axes of rotation. So let's first take a look at these ones on the top left, the thin rod. We see that when we rotate it about the center, it has some rotational inertia, 1/12 ml squared. And then if we rotate it about the end instead, the rotational inertia increases by a factor of 4. And that's because we increase the average distance that these mass elements are from this axis of rotation. In the first case, the furthest they can be away is L over 2. Right? Some of them are 0 distance away, and then they go up to L over 2. And in the second case, they can go all the way up to L. So half of this beam is now more than L over 2 away. So we've just increased the average R of these points, and so that moment of inertia goes up. The bottom left, this plane or slab about an edge, is extremely similar. Right? We rotate it about the center, we get one thing. We rotate it about the end, we get a bigger rotational inertia. However, notice that we have 2 dimensions for this planar slab. Right? We have A, which is the axis that is pointing perpendicularly to the axis of rotation, and then we have this length B, and that's the edge that is parallel to the axis of rotation. And if you look, B actually does not come into the formula. B does not factor into what the rotational inertia is of this slab. The reason being, it doesn't matter how long this plank is, right? Like we just mentioned, with the weights moving them up or down, that distance, the distance from the axis of rotation stays the same, right? It doesn't matter how far up or down, that's all parallel to the axis of rotation. All that matters is how far from that axis the mass is, which is described by A. And so if we look, the formula for the ones on the top left, the thin rod, and the plane or the slab, those are actually the exact same. And the reason being is that these two things are really the same shape. Right? They're both rectangular prisms. It's just like you squeeze one and stretch it to make the other. But they're all, rectangles on every side. And so, yeah, I think that's just kind of cool. Like these thin rods at the top, they still do have that like B axis. It's just small, and so it's not labeled. But those are really the same thing. So now a challenge question. I don't have a clicker slide for this, but take a sec to talk to your neighbor. Let's take a look at this thin rod on the top left. What would be the axis of rotation that minimizes the rotational inertia? So what axis of rotation, and not just these two, any axis in any direction in space, what axis would minimize the rotational inertia of this object? And if you finish that, think about what would maximize it. All right. What do we think which axis minimizes the rotational inertia of the thin rod? Anyone want to take a guess? Yeah. Exactly, yeah. So like skewering it right down the long axis. So on this page, it would be like sideways right through the center. because that orientation does minimize the distance through the average distance of all the mass elements. So that if you had a pencil, it'd be like spinning it around its like central axis would be the easiest to do. Okay, and now how would you maximize? Is there an axis that maximizes the rotational inertia? What did we think about that? Yeah, so that is the case. That's the maximum rotational inertia we could get with an axis that's touching it. But there's nothing that says we can't take this axis and detach it, right? Like the Earth going around the sun, it's rotating, it's revolving around the sun even though they're not connected. So I guess that was not a trick question, but you could put this axis infinitely far away and just make the R extremely big, and then that rotated around there, in which case it would just be like this rod rotating around in space on this long arc, which that would technically maximize it. But yeah, the axis you can put anywhere doesn't have to be attached to it. But if it was attached, then yeah, the bottom example here would be that. On the right side of the slide here, these are things we've covered a lot already, where you have a cylinder or a sphere, and if you take a hollow one versus a one where the mass is distributed all throughout it evenly, the shell, or the hollow one, is going to have a higher rotational inertia, assuming they weigh the same overall, just because we're taking the mass and concentrating it as far away from the center as we can, or as far away from the axis of rotation, I should say, as we can. So none of these you'll be responsible to calculate. As it's shown here, you need to do an integral. This is just like the calculus way of writing the sum that we had on the previous slide. So yeah, you'll never have to evaluate that, but you should be able to just kind of do this kind of qualitative reasoning that we just did here, saying like why one is more than the other. And then also, sometimes you may just be given one of these, saying like this shape about this axis is this moment of inertia, and then you can go throughout the problem normally by plugging that in. So questions about rotational inertia? Cool. So now we're going to do some clicker questions, and some of them are pretty tricky. So yeah, with these, give them a sec to think for yourself, and then highly encourage discussion here. All right, so first, we have a balanced seesaw. So in the before picture, this is in equilibrium. The torques are balanced. It's not rotating. And so what we do is then we take it with our hands, rotate it. So we don't give it any like momentum. We just rotate it and then let go. What's going to happen once we let go in this bottom case here? So for this one, it's good, like think about it like intuitively first, like what's your gut reaction? But then writing out the torque balancing, I think will help a lot too. Try to prove it to yourself and to your neighbors. For those of you watching this on YouTube at home, go outside to your seesaw and try it out yourself. Oh, we have at least one answer for every option. I'll give you 20 more seconds or so. Are you talking about the physical? Those are the biggest scam ever. They're like $40 or something crazy. That's how much I spent in undergrad on it, yeah, when like your phone works the whole time. Anyway, So the answer is A. It will stay tilted. And let's take a look at why. So looking at the before picture, the relevant forces, the ones that produce torques, we have gravity. I mean, they're both gravity, but we have the gravity on the plank itself, which acts at the center of mass. So whenever we're doing these torque balancing problems, gravity acts at the center of mass. And so for just a long plank, that'll be right in the center. And since this plank is off center, that is off axis, right? So gravity is applying a torque here, and that torque is into the page, right? That gravity wants it to rotate that way. And then the mass of the ball is providing a torque in the opposite direction, right? And so if it's in equilibrium, we know that these torques are balanced. And actually if these are the force vectors, then this picture isn't really, well, I guess it could be, whatever. But they're two forces that provide balancing torques. Then afterwards, once we tilt it, do the magnitudes of the forces change? Well, does the mass of the plank change? No. So this gravity vector on the right is going to stay the same. Does the mass of the ball change? Also no. So the force vectors here that are producing the torques do not change at all. Do their distances from the pivot point change? Also no. We're just taking like some distance and rotating it, right? Since it's rotating about the center, we're not changing that distance at all. Yeah?
I was curious about the distance. So before the ball is hanging at 90 degrees, and then after it's more like this, would that change the distance?
Yeah, so well, it depends on how you think of it. If you want to think of it from like the R perpendicular, that does change. The actual, like, if we follow along the plank from the attachment point, or like where the vector is, to the pivot, these two distances along the green are the same. But if we look at the R perpendicular, just the horizontal distance, that does change. But so first I want to think about it just like in terms of the angle. So we've decided that F and R do not change, right? The vector F, the force vector, and the vector R that goes along the plank to where the force acts, those don't change. But as we can see, the angle between them does. So F perpendicular or R perpendicular, depending on which one you use, will change. So either R perpendicular shrinks in the bottom, right? Because as you rotate them, the vertical distance increases, and so the horizontal distance shrinks. We want to take this to its extreme, right? If we rotated this 90 degrees, these would both be perfectly in line with the pivot point, and they would have no horizontal distance, no F perpendicular. Or you can think of the F perpendicular shrinks, in which case some of the force is now pointing along the R vector, and some of it's perpendicular. Either way, the important thing is that these two angles are equal. So for both the torque produced from the ball and the torque produced by gravity on the plank, both of those will be FR sine theta. Same F and R as before, and the FRs are equal, right? We know those torques do cancel. And now we're just multiplying both sides by the same sine theta. And so if they were balanced before, they're still balanced at the end because they're both reduced. Both torques are reduced, but they're reduced by the same fraction. So that's the answer. I did get, last quarter, someone asked a very good question that actually stumped me in class. I had to look it up after. I didn't know what was going on. But if we think about like a balance scale, right, like the classic like justice thing, the whole point of those is that if the masses on either side are balanced, then it will go to the middle. Like that's how you know that the masses are the same, right? And if they're unequal, it'll tip. If they're equal, even if you displace it, it'll find its way back to equilibrium, horizontal. And so how does that match up with this, where we just described where if it's at equilibrium like this, horizontally, then when you tip it, it should stay there, not go back to equilibrium. And I wouldn't expect any, I was asked, like, how does this work? I couldn't figure it out. I mean, maybe you could think of this better than I could, but it turns out that it's something in the design of the balance scale. You can look it up for more information, but really what happens is the pivot point here has a bit of vertical separation, which, I don't know, it's hard to describe it. Look, if you're interested, look up like the Wikipedia on balance scales, I think is where I found the answer. Maybe it was like Stack Exchange. I don't know. Someone gave the answer, and it makes sense, but those do have a design element that makes them different from this setup. Otherwise, it would not tell you anything, those balance scales, and they would just stay unbalanced if that's where you left them. Okay, let's try another one. So you are at the center of a carousel that's spinning, right? So you're right at the center, and then you start walking radially outward toward the edge. What's going to happen and why? All right, so a lot of people have answered, and one answer is a lot more popular than the others, but now I'll put out there that there's actually two options here that are correct. So you don't need to change whatever you entered on the clicker, but see if you can come up with what two answers should be correct. Yeah. Good question. Let's say a line on the carousel. I think this still works, but I think, yeah, it could end up being a strange answer if you walked in a line. Yeah, I'll have to investigate that. Okay, so first let's decide what happens, and then we'll say why. So is it going to speed up or slow down? Slow down, yeah, that's the same thing as like me. So now I'm the carousel, and the weights are me, and so the carousel's spinning, whatever, and then I start walking radially outward, and I slow down. Yeah. Okay, so that's right. The first answer that came up, that was the great majority of answers, was D, which is the carousel slows down because the rotational inertia of the whole system increases, which is true, and that's kind of what the point of this demonstration was, that as I move the mass further away, the R increases, so the rotational inertia, moment of inertia increases, and since angular momentum is conserved, the speed must go down. That's true. However, B is also true, that the carousel slows down because I put a torque on it, and we could see so using a momentum chart, or an angular momentum chart, where here, initially, the carousel is spinning. Doesn't matter the direction, but let's just pick this way. So that would be counterclockwise on the page. We use our right-hand rule. I'm at rest, I'm relatively at rest. Maybe I'm like rotating in place, but my R is 0, and so my rotational inertia is about 0. And so the initial angular momentum is just that of a carousel. Then, as I walk outward, I gain some R, some distance from the axis of rotation. And so my rotational inertia, goes from 0 to some positive value. And now I also gain some angular speed, right? As I walk out, now I'm going to be attached to a piece of the carousel that is moving, and so I'll move too. And so I know that I'll pick up some angular momentum in the same direction that the carousel originally had some. And then since I gain some, and the total change has to be 0 because there's no net external torque, whatever I gain, the carousel has to lose. And so we end up with me with some now new positive angular momentum, and the carousel with slightly less than it originally had. We exchanged angular momentum. And so what does this change in angular momentum, this middle column, come from? It comes from torques applied over time. And so maybe it's harder to see, like in a collision, things just collide, and maybe it's kind of obvious to think about like when they hit each other, they apply forces on each other. But actually, as I walk outward on the carousel, we're also applying torques on each other. When I put my foot down and take a step further, that force that I'm putting in to propel myself ends up having a perpendicular component and applies a torque to the carousel. And this is where it comes in, where it matters whether I'm walking in a straight line with respect to the carousel or whether I'm just walking in a straight line with respect to the ground. That's kind of like, if we take the two extremes, if I'm walking completely radially with respect to the carousel, or if I turn and almost run on it like a treadmill, where my distance won't change and I'm just like letting it pass underneath. I don't know, we don't need to get in the particulars of that. But it does matter just like the direction that I'm walking, because that will affect the direction that I'm applying force with my feet, and thus the torque that I apply. But anyway, as I walk out, I apply a torque on the carousel, and of course, the carousel applies a torque on me. And so it's also true that the carousel slows down because I apply a torque on it. Yeah? Yeah, so let's maybe try writing this on the board. So I'm just going to draw like a circle for the carousel. And here's the center. Can you see this? So here's us walking up like that. And so to walk forward, and so like this is it gets a little tricky here. This is like from the perspective of the carousel. So this whole thing is rotating. So actually, as I move forward, this point is moving in space. So from like the outsider's perspective, it's going to like kind of follow like a spiral type of deal. And so when I walk outward, it does look like it's completely like has no perpendicularness. However, in order to stay on this line, there's actually, I am walking with respect to the ground, like with respect to like the outside that's not rotating, I am applying a sideways force. And you can feel that if you have access to a carousel. If you try to if you pick a point on the carousel that's radially outward and you try to walk toward it, you'll notice that you have to lean to counteract it. And those forces are very real. So yeah, that's where it would come from. Okay, more questions here? So yeah, these answers are both correct, just depends on the way you want to look at it. I would say D follows from just considering the system as one piece, as one thing, and you're changing its rotational inertia, right, moving the mass further away. B is thinking of this more as a collision problem, where you have two objects exchanging angular momentum and applying torques on each other. But those things they fit together. They both mean the same thing. As always, you can just frame problems differently, depending on what makes sense for you. All right, another one. This one starts to get a little challenging, well, continues to be challenging spatially. We have a girl on a carousel again, and now it's rotating with this angular speed vector. So she's attached to it, and she's got a heavy ball, and she wants to throw it in a way that will make the whole thing come to a stop. So which way should she throw the ball from this perspective at this time? I'll give you 30 more seconds. Is it? Wait, say that again. That's saying that the current angular speed. So before she throws it, the angular speed is pointed that way. So no. Yeah. So you can still do that. We'll go over it. Well, let's do that now. Okay. So first, let's identify like what this omega vector that we see means. So it doesn't mean there's a torque yet. So before she throws the ball, there's no net torque. This is just a system that is rotating with some constant angular momentum, and it has some constant angular velocity omega. So if we use our right-hand rule, this is kind of like backwards. We point our thumb with omega, and then our fingers wrap in the direction that it's going to rotate. So it's going to be like this way. Or from our perspective, if we're looking at this, it'll be clockwise. Which means that at this moment, the girl in this position is coming out of the page. So that's what this omega is saying, is like what's happening beforehand is it's rotating clockwise, and she's pointing, her velocity, her linear velocity is pointing out of the page right now. And then we want to ask, what do we need to do in order to stop that? So from an angular momentum perspective, we have this angular velocity and angular momentum that's pointed down. And so to get that to 0, our change needs to be equal and opposite that, right? We need an equal magnitude vector that's pointing up. So we need to apply a torque that is pointing up. And so if we use our right-hand rule for that, point our thumb up, wrap our fingers, that gives us, of course, something in the opposite direction. This torque is going to push counterclockwise, which at the location of the girl means that the torque needs to come from a force that's pushing into the page, right? In order to cause a torque to stop the thing that's rotating clockwise, we need to apply a force in the counterclockwise direction, right? So that would be, we need a force that's pointing into the page. But we're not quite done yet, because we need the force to be into the page, but that's not what the question's asking. The question's asking which way should she throw the ball. And so if we want to produce a force that's into the page, we need to have her throw the ball out of the page, because then she'll give the ball momentum outward, which will give her momentum inward, right? That will be her force, an equal and opposite force into the board. So she actually needs to throw the ball out of the page. Right? So if we work backwards, she throws the ball out of the page. So the ball, she causes a force on the ball out, which causes a force on her in. And if we look, a force pointing inward at that location is going to provide a torque upward, which cancels out the angular momentum that we started with. The other acceptable answer would have been whatever direction it is to the carousel operator, which also would have worked if she threw the ball at them. Okay, now let's do another one. So this next question is a lot like this one, new situation and kind of rotate it around, but see if you struggled with this one, see if you can learn from it. So now we have a helicopter, and the main rotor, like the top propellers, are rotating as shown. And so we want to know what direction must the tail rotor produce a force in order to keep the main compartment, like the body of the helicopter, from spinning. And to make it, you can think about like maybe the helicopter's like nothing's moving, it's just floating in the air, and then we start this main rotor spinning. What do we need to do to keep the body still as we start the main rotor or increase its speed? What'd you say? No, you can ignore friction. Well, you can't. It's not really friction, but they have to be connected in some way. So that's a good question. If there was no friction, how would they even like communicate? I guess. Yeah. So I guess you wouldn't say it's friction, but they are just connected, right? Because otherwise, how would you spin the top rotor unless it was planted, right? So there's some assembly in there that's spinning it around. So it doesn't matter if there's friction, but they are they're just connected and they can rotate. All right, let's go through this one. So first, why do we need the tail rotor in the first place? So we know it's like to keep the body of the helicopter from spinning, but why does it spin? So I have to pass, the answer's left, but we'll work through there. So let's assume there's no tail rotor. So initially everything's at rest, or maybe they're rotating, it doesn't matter, and then we speed it up. But either way, what we're doing is giving the main rotor some angular momentum. And the direction that we've drawn it here, that would be into the board, right? We wrap our fingers clockwise like this, and we get into the board. So if we give the main rotor angular momentum into the board, but the total change is zero, right? There's no external torque, nothing else is acting on the helicopter, then there must be an equal and opposite angular momentum change for the body of the helicopter. And that's not, right? So if the main rotor is rotating clockwise, as soon as we start rotating it clockwise or increase its angular speed, the body is going to start rotating the other way. Not as quickly, because the rotational inertia of the helicopter, it's much heavier than the rotor, is going to be a lot higher, but it will start counter-rotating, which is not what we want. We don't want the people in the helicopter to be rotated every time we change the speed of the main rotor. So we're going to use the tail rotor to cancel it out. And what change to this momentum chart do we need to make in order to allow the body to stay with zero angular momentum the whole time, which is what we want, right? We don't want any rotation from the main body. And so to do that, if we enforce that the top must be all zeros, then the only thing that's left is that there must be some external torque, right? And that external torque must be into the page. And so if we need to produce a torque that's into the page from the tail rotor, right? Into the page would mean, again, clockwise. And so if we want to produce a clockwise force at the location of the tail rotor, that gives us that the direction is to the left, right? Because our R vector points from the center down to the tail rotor, and to rotate it clockwise or provide a torque into the page, the force needs to be this way, which means it's pushing air the opposite way, to the right. But the force on the helicopter from the tail rotor is to the left. So this one's kind of, I think, the phrasing, or maybe the phrasing or just the problem setup, it's a little strange because we find that the initial angular momentum of the main rotor is into the page. And so we'd think we want something like opposite that, right? But it turns out that we want to provide an angular momentum into the page. And the reason that is the way I like to think of it, is that what we're doing is the tail rotor is dumping angular momentum into the system, and it's being transferred to the main rotor. Like the place where we're getting, like the main rotor needs angular momentum to spin, and instead of getting that angular momentum from the body by spinning it in the other direction, we just get it from the tail rotor, which is pushing against the air and getting that force. We don't care if we push the air really far away. That's fine, right? So yeah, it's just the body is acting as like a conduit between transferring the angular momentum that the tail rotor gets up to the main rotor. And if the main rotor wasn't there, of course, the tail rotor would just cause the main body to spin instead. But there's these two kind of like balancing each other. Yeah.
So if the torque is into the page, why is the force required going to the?
Because here's the R vector, right? That's the axis of rotation. If we wrap our fingers in the direction that this force wants the helicopter to rotate, we'll get into the page. So this force in this position produces a torque. that's into the page.
Oh, I was thinking of it of like looking at the propeller from the side.
Oh, yeah, the side view, then it would be like depending either into or out. Yeah, so it gets complicated really quickly. Yeah.
So if you're calling that like going to the left,
Mm-hmm.
wouldn't you call it like, is it just like one bar that's rotating?
This is another propeller. So if we looked at it head on, it would look like the top main rotor.
So if we're looking at it from this side?
If we're looking at it from either like here, like in this plane, or here, it would just look like a fan that's spinning and pushing air, and that's why it can create the force like that. Which adds another thing. So the way the tail rotor spins, right, that's its own angular momentum, which is in the direction of this force, right, to the left or the right, depending on which way it's spinning, right? And so this angular momentum vector, or like the axis that's going left to right, that corresponds with the whole helicopter flipping end over end, right? So like this thing's spinning, this tail rotor is spinning into and out of the page like that, which is an angular momentum vector like this. If we ask what direction of spin is it when we take like the whole helicopter and say it has an angular momentum vector to the left or the right, that's the helicopter rotating like into and out of the page end over end. So I think it balances out just fine, but maybe that has something to do why helicopters kind of like, travel tipped. I mean, that probably has to do with just the way they actually move forward and backward, but there is some torque produced by this tail rotor that will make the helicopter tip. Maybe that's the way they tip. I don't know. Okay. Yeah. If the force from the tail rotor was pointed the other way, then the helicopter would spin even faster. Because now, if we look at the momentum chart, we'd have an external torque, a total change in L, like in the bottom middle, that would be out of the page. And then so what we'd have to add to this into the page from the main body to get to out of the page would be a really quickly spinning body on the top. That would be like a really big out of the page. Then the people inside would be really screwed. Yeah. Any other questions on this one? Okay, so now let's do kind of a fun example looking at the precession of a top. So I'll try to play this YouTube video really quickly that demonstrates it if you don't know what we're talking about. So feeder mode. Okay, so yeah, when you spin a top, and despite the name of the channel, this is not mine. When you spin a top, not only does it spin around the center axis like we'd expect, but it also, it's called precesses, where like the overall axis of rotation of the top goes around in like curve, like traces out this circle in the air. So that's the effect that we want to describe. Like, why is that happening? So let's go back to the slides. So here's our top. It's spinning. And actually the direction, so has some angular momentum. These two don't match, right? If you wrap your fingers in the direction that I drew the spin here, that gives us an angular momentum pointed the other way. But just assume the pink one is right. So imagine the top is spinning the other way. This is just a mistake. But assume our angular momentum. Either way, it's going to be along this axis, right? This is the normal spin of the top, just spinning around its central axis. There's our angular momentum. That doesn't require, it requires a torque to start it, but once it's spinning, it has that angular momentum, constant, it's fine, it'll stay spinning. But there's other forces that are always going to be at play. What other forces are acting on a top when it's spinning on a table? Gravity, yeah. And gravity acts at the center of mass, right, and straight down. So we have this force due to gravity that's pointed straight down. And there's one other force. Why doesn't the top fall through the table? There's the normal force, which I don't have it drawn here, but the normal force is going to act right at the bottom point where the top meets the table. And does that have any moment arm? No. So what I'm trying to say is that doesn't produce a torque. That's right at the pivot point for whatever axis this top is rotating. And so there is a normal force, but it doesn't come into play when we're talking about the torques right now. So back to this force of gravity. The axis of rotation that we looked at for the first L vector of just like the top spinning around its central axis is this diagonal axis here, which along that axis, gravity does not provide any torque, right? Gravity is not going to spin this top any faster. But it does make the top want to rotate in some direction, right? And that direction is just like tipping over, right? We have some r vector from the pivot point up to gravity. And so what gravity wants to do is make the top fall over, right? If we, like just anything, if you like tip it over and then let go, it's going to fall because gravity is pulling on it, applying a torque, and making it rotate down toward the floor. And so the direction of the torque produced by gravity is, well, into the page. But I guess if we really want, we can see that not all of gravity produces a torque, right? There's a perpendicular component. Some of the gravity just pushes right along the r vector and just like pushes this into the table. But some of it does make the top want to fall over. But regardless, we get a torque that is into the page from gravity, right? That's this falling over torque. And so if the torque is into the page, then the change in angular momentum is into the page. So there's an angular impulse given to the top by gravity acting on it. So now we have an L initial, which was just the top spinning around its own axis, and now a delta L that is into the page. So now let's change our perspective. Let's look at this from the top down. And if we do that, so on the left, this is the same picture we had before. If we look at it from the top down, we see that our L initial, that's along the axis of the top, is perpendicular to our delta L. And if we add them together to get L final, we get like a rotated L initial, right? We just rotate it. And if we did this again, now gravity's still acting on it, the delta L is always going to be perpendicular, and we're just going to get the L vector that precesses or rotates around in a circle, which is exactly what we observed. So, I don't know, I think it's pretty counterintuitive that like when there's no, so I guess I have a slide on that. What if the top was not spinning? If we lacked that initial L vector, then gravity would provide the same torque, and now our delta L gets added to 0, and so our L total is just into the page, and it continues to be, and the top just falls over. But when we do have this initial L vector to add to, we get a different effect, where instead of falling over, the magnitude stays the same, and it just rotates around, and that's why we get the top spinning around. In reality, there's like friction and stuff, so that's why after a while it changes and will fall over. But in an ideal world, it would just keep spinning in a circle like that. I don't know, that's kind of cool and counterintuitive, and I think it's a pretty like complicated effect, but all of the work we've done, like we have the machinery to talk about it. Our torque framework perfectly describes this. And if we wanted to, we could do this quantitatively. We won't, and I won't, in general, I won't assess you on problems where there's like angular momentum in like 3 dimensions, because as you can see, it gets pretty tricky. But, you know, it's possible. I won't take a lot of time to talk about this, but hurricanes and like planes flying in the sky too is something called the Coriolis force, which the origin of it is very similar to what we just talked about with the top, and it comes from the Earth is spinning, right? And so we have some angular momentum, and when we travel along the Earth, this is like in the air, not connected to the ground, there's a force from gravity that's always pointing to the center of Earth, right? The axis the Earth is spinning around is this tall axis through the middle of Earth, and gravity points diagonally to the center, and as long as you're not at the equator, there's going to be this perpendicular component. There's going to be a torque that's applied by gravity. And the result is that you get these weird deflections. When you're in the northern hemisphere, you always deflect to the right in this kind of like clockwise shape. And if you're in the southern hemisphere, you always deflect to the left, regardless of what direction you're going, which is how hurricanes move and how they rotate, which I think is kind of cool. If you want like a YouTube video or Wikipedia or something, again, just to like see really how the effect works, see if it makes sense to you. But again, this is all just like weird stuff that happens when you add angular momentum vectors together, because the results can be counterintuitive, even if they do follow the laws of physics. All right, final thing, this is more applicable to what we'll actually be doing. this simple case here, we have a plank that can freely rotate about the center, just sitting there, and a ball that's going to come across in a straight line, hit it, and then it sticks. And we know what's going to happen is once it hits and sticks, if the pivot is like pinned to the center, it'll just start rotating, right? And so the initial case where the ball is moving horizontally, that would be easier to describe, probably with just linear momentum, right? Just mv to the left. Great. But then the final case where it's rotating around, we probably want to use angular momentum for that, right? Because otherwise then like the ball is moving to the left at the top and then down and then to the right and then up, and it's always changing. So the linear momentum way to describe it is not super helpful at that point, or not super interesting. And so how do we bridge these two ways of thinking about this problem? How can we connect them? Yeah, because they both will be useful at different times. Well, let's just take a look at a ball traveling in a circle, right? We know that our circumference of the circle is 2 pi r, and the time to travel a certain distance is just delta x over v. So we can calculate that the time for the ball to go around once in a circle and relate it to its linear speed, v, right? We know we studied circular motion a little bit with like the tennis ball on the string, and we know that when something's moving in a circle, its velocity is perpendicular to the circle. And so we just get this time for the ball to go around completely is 2 pi r, the distance divided by the velocity. Now we can connect that to angular velocity, which we know is just the change in angle over the change in time. Change in angle is 2 pi for a complete rotation. We just find delta t for that related to v is 2 pi r over v. And so we get this neat expression that our angular velocity is just equal to our linear velocity divided by r. And we can see the units work out. Omega is 1 over seconds, and then we get meters per second divided by meters. So we also get 1 over seconds. So now let's connect this to angular momentum. We have our omega equals v over r. And sorry, we're running out of time, so I'm having to rush. But the only other piece we're missing for angular momentum is our rotational inertia. For just a single mass, a distance r away, that's just going to be mr squared. And so we multiply that by our angular velocity, and we find that our angular momentum of an object, in this case, is mvr. And then we can connect that to our momentum, which we know is mv. So our angular momentum ends up just being our linear momentum times r. And more generally, as you may have expected, what matters is not just all of the angular momentum, but just the perpendicular piece. So either r perpendicular times p or r times p perpendicular. In the case I just showed here, it didn't matter because they're already perpendicular. But you can imagine a case when they're not. Just like the example where I just showed with a ball traveling toward a plank, where we can see that r and v are not perpendicular, and they're changing over time. So maybe I'll start here next time. You probably won't actually have a question on this, but it might come up in DL a little bit. But I don't know. It's worth taking a look at. I'll see you next week where our quiz will be on torques and angular momentum.